You don't always have a server, right? So now if you want to do that, then you need to write down mathematically. So now in the case of federated learning, as I told you before, this is a minimization of this empirical risk here. These are the loss functions of all the devices, right? This is the consensus, right? Because this is a consensus optimization problem. And now once you go away from the centralized approach, you end up with a lot of techniques, right? So now one of the techniques we actually exploited is this idea of group ADMM. So ADMM, I'm sure some of you have maybe used it. It's a primal dual optimization technique where now I have a set of devices, right? Which I'm going to split in several groups. In this case, we divide them in terms of two groups. You see the purple group, the yellow group here. And then by design, in fact, if you want to solve this mathematically, you will see that some devices in the head group have disjoint set of constraints. This allows essentially to decouple the problem here. So for instance, you have this device here. What it will do, it will just update its primal variable, send it to two workers, right? T2, T4, these are workers in the other group. This guy updates his primal and dual, and then send this back to the other group. Okay, so a very basic actually problem. Here the difficulties in this kind of problems are the proofs. You can spend 6 months to prove that the algorithm converge. This is one of those works, you see. So mathematically very simple to formulate, but again the difficulty is in proving that this algorithm does converge. So I don't know if I have time to go through the mathematics. I mean, this is very basic. I mean, you just write down your augmented Lagrangian, right, and then the primal variable equation for the head workers, right, and then the tail workers, and then the update, right, of the dual, right, and then of course again you need to prove that asymptotically the primal residual and dual residual converge to zero, and of course the optimality gap converges to zero asymptotically. Okay. Now, in terms of results, of course, so this is classical in machine learning, right? You plot the objective error or test accuracy, or okay, as a number of epochs or number of iterations for a lot of baselines. So here, these are baselines already from 2020, I think. So you have gradient descent, you have variants of federated learning, how many iterations you do locally, how many iterations you do at the server. But you look at, once you go away from the server, look, you achieve a much faster convergence, and you achieve even much better, let's say, test accuracy. This plot here is to show the impact of this penalty disagreement between the workers or the clients. It's called rho here, because that's a parameter that actually reflects the fact that the data is skewed, right, or power tailed. Okay. We also try to look at the case where we go from a static setting, meaning you can allow some devices to change their neighbors every now and then, but I'm gonna skip this for now. Okay. Now, what's next in this type of works? I mean, it's a mindset, right? So now the question is typically, the question to ask is, can I now compress my model, right, without losing accuracy? This is a classical question we pose in machine learning. Again, in a communication efficient, of course, machine learning. The problem now, I take the same setting as before, but now I want to compress maybe down to 2 bits, 1 bit, 4 bit, right? And see what kind of hit I take for my accuracy. Now, once you do this, again, mathematically, you have to be careful because there are some errors when you quantize your model, and because you communicate with your neighbor, these errors tend to accumulate over the graph, which means it doesn't converge. So you need to choose your resolution range, right, and resolution. These are the delta here and R here. And then you need to use typically a unbiased stochastic quantizer to make sure that the error decays asymptotically. Maybe if you look at the results here, this is again the loss, number of communication rounds. So this is essentially so the quantized version with 2 bits, okay? And this is, on top of it, you have the full precision, so 32-bit model compared to 2 bits. No loss of accuracy. What's even more interesting, obviously, is, this is, one part of the story. The other part is, look, when you go from a full precision to 2 bits, you have a huge savings in terms of how many bits, of course, are transmitted over the air. So again, in this particular setting, of course, it's a free meal, right? You don't lose anything in accuracy. In general, you do tend to lose, but again, this is depending on the data set that you have and so on. Okay? We also try to extend this a bit to relax some of these constraints. For example, here, this was a chain topology, right? Chain. Now, what about if it's a bipartite graph, so you can allow more neighbors here? Here is 3, here was only 2. But you could also look at cases where now the worker, the device, does not have to communicate every time with the neighbors. Maybe it has nothing valuable to say, so just keep quiet, right? This is this idea of censored quantized GGADMM. So we developed again this technique, again try to compound, right, the fact that you leverage temporal sparsity, so nearby devices, but also don't communicate very often. This is the constraint you need to satisfy when you need to communicate, okay? And the gains are very, very, very big in this case, okay? We could also look at, this is something very open still. Once you go away from the star topology, so federated learning server is a star topology, right? You have a node in the middle and the others are around it. Once you go away from this scenario, there are a lot of problems that need to be solved. So for example, what happens if you have, you go from a sparse to a dense graph? Is convergence faster, not faster? Now this may be better for example, but it's not resilient. If you have an attacker here trying to block some links, it will hurt the performance of the model. This tends to be better, but it incurs more overhead for communication. Which one is the best? It's still an open problem. But anyways, and now what you can do, of course, take all my works and try to extend them bit by bit and publish in actually the best venues in machine learning are really possible. Okay, this is my key message number 1 today. So again, you can take this, extend them to maybe second order methods. So this was a first order method. Now the trend is to go from second order method. This is a recent work, ICML. And then of course you realize, okay, Bayesian learning actually is more powerful because it gives you uncertainty quantification. So all these works actually they tend to overfit, meaning that they don't know when they don't know. Okay. However, Bayesian learning is by design a technique that allows you to deal with uncertainty. Okay. Of course, this with supervised learning, you can push it for RL, and just keep in mind, so accuracy is just one metric. Maybe it's not the most important, right? You have energy, you have robustness, you have generalization, you have different metrics that have not been exploited. We jumped as a community on this metric, and we were competing, who's the best. But in fact, once you put this in the design, you realize quickly, actually, I need to push this down, not up, okay? Okay, so and now, of course, now I'm gonna move on a bit to the co-design. I told you before there is this dichotomy between, digital federated learning here. For example, you guys, if you want to model this using, modeling the links between the device and the server, you model it, okay, what kind of channel fading I have, what kind of path loss, right? But in federated learning, the problem is this number of devices here is huge. It's a couple of thousands, right, or millions maybe, right? So there's no way you will be able to find a wireless resource to transmit your model to the server, right? You can do it, but it's more cost that you need to pay. It turns out, as I told you, because in fact, if you adopt a more analog type of communication, the server doesn't care. He doesn't want to decode every worker model. It wants the average, okay? That's the reason. So by casting this as an average, let's say, consensus problem, even if one device doesn't communicate to me, no problem. And here I just leverage the additive addition of the wireless access channel. So that's a bit what we did, again, mathematically here. We formulate this mathematically, again, the same setting as before. This is a digital version of it, but now what we do, we encode the channel, right? You can see here, this channel comes to play a role here. This very basic addition here, actually, once you develop your augmented Lagrangian, primal and dual variable, it creates problems for conversions. So you need to take care of those things, and it may take a couple of months, but we eventually did it, so that's fine, right? But again, here you can really now try to do this now looking at energy, looking at reliability. We haven't done that, so why not? So this is basically the idea again. I mean, just to, the workers again communicate here to the server. This is the conjugate of the channel plus the dual variable. So the server gets this, pushes this to a match filter, gets the average, and this iterates. I think what's more interesting here are the results. So now for image classification, you see this is test accuracy, number of communication uploads. This is the digital, okay? Look how slow it takes to converge. Look at the analog, it's extremely fast. We were even nice with the digital, we gave it, I think, 10 times more bandwidth. Look, it's still struggling here to come to terms with the analog, right? So bottom line, why don't you use this technique? I think it's a much more powerful one. Even in terms of energy efficiency, this is the analog. Look, for signal to noise ratio, the digital approach needs a very high SNR before it starts to converge. Again, why not use this technique, right? Okay. Again, now moving a bit now forward. So, I mean, as I told you, it's a zoo of techniques. So now I'm walking you through the, the various. So this is another one. This is a collaboration with MIT. Essentially here we said, okay, what about now if we put all the burden, these are maybe watches or sensors or microcontrollers, because once you do federated, it means that you run some iterations of, your gradient descent or stochastic gradient descent, which consumes power. Why now let the server take care of that problem? But you need to make sure that now this data that is communicated from the devices to the server is blurred, right? It's privacy preserving, such that when the server trains a model with this blurred, noisy image, it finds of course the best model for that. So here, this is more of a utility privacy trade-off in machine learning. So of course, if you don't care about privacy, fine, maybe the best user transmits. If you care about privacy, you need to take care of, I think it's here, you see. This is, for example, okay, I have 16 devices. You can see here, to get a blurred image, I need to tell I cannot know which device actually has transmitted. That's by design, okay? Whereas if I don't care here, look, I ask worker number 12, hey, communicate your data. I need it to train my model. So again, this was more of an analytical exercise. We try to find essentially what is the, because here we use this framework of differential privacy in machine learning, right? So it's characterized by 2 parameters here. Again, utility privacy trade-off. We characterize this as a function of transmit power. How much power should the device communicate its data such that you maximize your utility accuracy, or you care only about privacy. So again, I don't want to spend much time on this. Maybe you can look here at this table. This is privacy level. So when it's very high, look at the accuracy. Very, very poor, right? If you don't care about privacy, okay, that's fine too. You get a much higher accuracy, right? So again, it's really a basic exercise to capture this utility privacy trade-off. So, all right. And of course, as I told you already, accuracy is just one metric. But don't forget fairness, don't forget robustness. So we had this very recent work actually here at Transaction Machine Learning Research, where again, basically we just adopted this technique of distributional robust optimization. Again, well known in centralized optimization, right? And we try to federate it. So again, this is where things surprises emerge. If you want to solve to prove that the algorithm converge, but you can do it. I mean, this is, as you can see, the algorithm is extremely basic. For people familiar with the risk-sensitive game theory or risk-sensitive reinforcement learning, there's this very nice idea of, instead of using the loss function to train, I use an exponential, right? And I put the loss here. This is the trick, because it gives you not only the mean, but also the variance of your loss function. And that's what we actually showed here. Number of devices, worse test accuracy. So we are pushing people, to the right. This is classical federated learning. It doesn't care. Some clients are left behind. Well, we're trying to push them here. But again, there's a cost to pay, accuracy, fairness trade-off. Okay, good. Now, another technique is federated distillation, as I told you before. So, I mean, the idea is very, very simple. Again, here what we want to do is we do not want to communicate the whole model because I don't have enough capacity, bandwidth. So what I do, I will actually transmit what I call a logit. A logit is essentially if you feed an image of a cat or a dog to a neural network, typically you have this histogram here, is 20% dog, 80% cat, that usually you squash through a ReLU to get cat dog. But you lose a lot of information. So why not use this basic histogram here that you push through now to the server, and then the server will try to help or distill knowledge, right? This is about knowledge distillation. This is about teachers teaching students to the student. So the student here essentially has to take, so this is the equation of the model update. Typically we don't have this term, it doesn't appear. All right, this is your weight, this is your learning rate, this is the gradient, right? Now what we add the regularizer, which is structured, which means that if the prediction between the student and the teacher is the same, well, you don't add anything. If it's large, well, guess what? You add it, right? Very basic idea. So that's actually what we did here. And the results were very, very interesting. So now if you want to compare federated distillation and federated learning, this is a sum communication cost, number of devices, test accuracy. So you can see here that in terms of communication cost, it's like 10,000 times less, right? However, we lose. There is a gap here between, you see, 92% accuracy to 86. There is a gap that we lose, but actually later on we kind of recover this gap by combining the benefits of federated distillation in the uplink, okay, and federated learning in the downlink, kind of a mixture of these two techniques, and we can actually show that we can bridge this gap quite easily, actually, okay? All right, this is the proof for those interested in proof. So yes, we can actually use this very nice idea called neural tangent kernel, which is actually just a kernel that holds when you look at infinitely wide neural networks under gradient descent. But what it's actually just showing is, given the teacher's model, right, how many iterations it takes for the student to converge to the same performance as the teacher. Okay, that's basically the idea. Okay. Okay, and of course now energy, right? I mean, we talk about carbon emissions, climate change, and so on and so forth. So we run a basic campaign of comparing actually, you know, the energy footprint of federated learning, centralized learning, federated learning, right? In terms of different topologies. And we found very, very surprising results, because of course people think that just by using federated learning, it's for sure more energy efficient than having one data center. Well, it turns out it's not always the case. Of course, that's maybe expected answer. But essentially what we found out is when the data is IID, okay? So every device is the same. Okay, in that case, of course, it's more energy efficient because the devices should not communicate all of them their model. One device represents the whole population of devices, and therefore you are more energy efficient than having a data center. However, and this is a surprise, if you are in the non-IID setting, which is the real world setting, you can see, for example, here, it takes, for example, if you put yourself, this is 90% test accuracy, it takes you 43 rounds of communication if data is IID, and it takes you, 62 rounds if it's non-IID. Why? Is because in the non-IID case, think of it like a tail distribution again, right? The device is living on the tail of the distribution. They have to constantly send their model to the server so that they are not forgotten as part of the model, right? And of course, here typically when you want to compare this carbon footprint, there are a lot of factors that we should take into account. For example, is your country based on renewable energy, solar energy, right? There's a lot of factors that actually give us a much better picture. Here, this is really a basic comparison here. I think we use Italy, France, and another country, EU actually, because we had the figures, right? Maybe if you run this now in a different country, you get the opposite results. We don't know. What we know, of course, is energy is an important metric, right? Okay, good. Another technique called split learning. So I don't know if you are familiar with this technique. It's a very nice technique because essentially what it does is it takes a model and it divides it in terms of, you decide I have 10 layers, I divide it in two, so I have 5 layers. You just run compute over 5 layers and the rest in the server. And the server, what it does, it helps you continue training, and then it sends you back the data because this is a medical hospital. You don't want that somebody has access to private data of people. So you have this boomerang effect, right? You can see it here. In wireless communication, we see it already. When we do joint sensing communication, right, with the server, this is already using a split learning. So how many layers I have to put here? How many layers I have to put here? What's my latency budget? What's my capacity budget? This is very interesting for students, okay? But for us, our application was actually the following. We wanted to use cameras in a factory, right, to help predict when a channel is blocked before actually it happens. Okay, so if you wanna, this is the received power, right, of the signal. Let's say, over time, you can wait until the signal drops and then you do something, right? Mobility handover or whatever. But here we want to know that before it happens. And the only way to do it is to leverage, again, cameras you put in a factory to help you train faster, to learn basically the geometry of the factory. So we did it, essentially. We compared RF, image-based, and when you combine both. Here I'm combining RF signals, and I'm also using camera images from the camera, which is on the wall in this case, okay? And then you train the model again, and you do the same thing you do. And then what you plot typically, again, this is a root mean square error, this is the cost for inference. And we wanted to actually deal with the very nice setting where, you know, people are concerned with privacy, of course, right? We said, okay, let me take now 1 pixel information, which is essentially when you go from raw image and you pass it through your CNN filters, you reduce the dimensionality 40 by 40, you get 1 pixel. If I use 1 pixel information with the RF signals, I am here, which means actually I'm better than if I only use RF. Okay, so RF only gives you the red curve. RF with 1 bit information gives you better performance. Now, if you don't care about privacy, let's say, well, you can see there's a nice optimization point here, right? Local minima or global minima, 4 by 4. This is the best in terms of how much I compress and how much I communicate. And that's essentially what we did. We try to also extend it to more than 1 camera, right? So this is very nice again because you have different cameras, different specifications, cheap camera, expensive camera. You cannot use federated learning here. Federated learning works only when you have the same architecture, the same type of specification for the device, then it works. So we use another technique called manifold mix-up. So I mean, just for those who are interested, this is about taking the internal representation of your neural network, right, and try to mix them up, meaning to generate more data from your internal representation. If you do that, then you can actually see maybe here, again, this is test root mean square error. When you do it for line of sight, non-line of sight, it significantly actually outperforms federated learning. And this research now is very important in beyond 5G, 6G, and so on, okay? Okay, and then now, of course, as I told you before, you could push this in reinforcement learning. So reinforcement learning actually is the tool that should be used because typically in life, you don't have a lot of data, you don't have a lot of label data. You can spend time and money to hire people to label data for you, but it's not really a reality. Instead, reinforcement learning by design allows you to, to do that real time, right? To sense, control, and make a decision. So we look at some problems here again, comparing digital federated RL, analog version, and analog. Yeah, this is with our approach. This was just a baseline. And again, as expected, again, of course, when you do federated learning, you improve. But here we compared, I think, yeah, with a bunch of baselines. Again, when you leverage this analog idea of communicating the models in 1 shot or 2 shots, it's much faster than if you do it with a digital approach. Okay, I'm actually getting to my conclusion, but not really because I have some other stuff. But yeah, so I mean, my message here today, okay, so this topic of edge AI is very, very popular. Maybe it's too popular, meaning that it doesn't force students to think. And I think this is the missing part in not only Morocco, actually it's all over the world. So regarding that, I mean, again, a lot of research needs to be done even within what I presented to you. For example, the robustness, the energy, the privacy, you don't find one work capturing all these trade-offs. You only find one capturing maybe just this or that, or, we need this. And this is an easy type of publications that you can actually target, right? But I am now reaching a conclusion, which is we need to actually, instead of going for incremental approaches and doing what the same people do, we need to step back. Actually, we need to go back to foundations of mathematics. And this is, I believe, something that Morocco in particular can play a big role, not just following the trends because it's trendy, right? So of course, theory, application, privacy, compression, and so on and so forth. But what do I have in mind? In fact, what I presented to you today is, for those who have read this book, Daniel Kahneman, Thinking Fast and Slow. This is a very important book for many reasons. He's a psychologist, but that's not important today. Essentially, all the machine learning you see today around you, you read, you reproduce, you base your research on, are called System 1. Okay? So System 1 is pattern matching, learning statistics from data. It's not really what your brain does. That's not what it does, okay? Again, curve fitting, more data, the better. Small data, big data, it doesn't actually matter, okay? Again, this is useful for some applications and people make money out of this, but actually it turns out the human brain has another cognitive mode called by this guy system 2. And this system is the one that you use to reason in your daily life, to plan, to think outside of your, trained distribution, right? It handles exceptions, it reasons, okay? So now, of course, I mean, going from system 1 to system 2 is really the goal. And in fact, you can combine these two, because sometimes the knowledge you have acquired here, you pass it here, kind of an inductive bias, right? Because machine learning, at the end of the day, it's a bias variance, you can call it trade-off, right? Whatever knowledge is acquired, push it here. So next time I've seen this data before, okay, I know how to solve this problem. But again, the limitations I told you already, there are many. So of course, the poor generalization of machine learning. So Bengio and others, they preach this every time, right? Federated learning, again, is one of the first step of really intelligence. Don't think that this is what we will be deploying in base stations and so if you put this in autonomous vehicles, it will not work, okay? It will crash. I told you the reason, sometimes because knowledge is not in the data. I can prepare for you today a data set with 1 billion data point with 0 value. And you take it and train a model and publish and graduate. That's not what we should be doing. Because in fact, what we need to go after is what we call so reasoning, extrapolation, imagination. Imagination is digital twin type of techniques, right? Abstraction. So humans abstract, right? We form concepts. We don't use data just to reason about it. We go from data to abstractions, okay? So we worked on this since COVID, actually. We came up with, let's say, 6 ingredients for a proper model. Because today what we do, we just use the first 2. The model, of course, has to be a function of the data. 2, you have to compress it because you need to store it, or because you need to communicate to a receiver. But what's really missing, the secret sauce is here. So 3 is symmetries. There is symmetry in the data. There is something we call invariance, equivariance. For people working in physics, this is very normal vocabulary. This tells me, for example, if I turn the image, it's still the same dog. So it's easy to do at the level of an image. But can you do the same thing at the level of a random stochastic process? Can you find me the invariance and equivariance there? This is much, much more challenging, and that's essentially what, let's say, autonomous vehicles need, but any other real-world mission-critical applications. Compositionality. So we need to do what babies do. Babies learn by interacting with the world, so it's self-supervised learning, it's not supervised. And they form concepts. So concepts are like Legos, yeah? You form concepts, and then depending on the goal of the task, you recombine these Legos to, build something else. We don't have this today in machine learning. Again, I told you why. It's a system 1, curve fitting, interpolation, and so on and so forth. Causality, of course, is very important. So again, you can do the same thing I did today. Of course, it will take more time. But yeah. Add these 6 ingredients for X. So X could be training a model, inference, reasoning, control, whatever, okay? And of course, we always have realistic constraints. So my application is mission critical, have battery, power, compute, bandwidth control, okay? Okay, so now what I am actually working on, this is my kind of awakening, is essentially that I realized that we need to use different mathematics. So today we have been using laws of probabilities, basically, statistics, right? But of course we know from high school, we hear about algebra, we hear about, topology. We have not exploited those things. So today, again, we are here. So we use entropy for, entropy minimization, or even in statistical physics, but also in communication and statistics, right? But first, you need to always ask the question, which I had said before. Before you start training a model of images, text, speech, whatever, you need to tell me first or learn what kind of topological space my data lives in. This brings us actually to realize that we have missed completely this aspect of topological spaces, okay? This is, for robotics people, this is gonna be common vocabulary, but in communication and machine learning, this is very much needed because now you need to if you learn in a topological space, you would definitely do better than if you learn in the, let's say, observable space, okay? And of course, how do you manipulate a topological space, okay? You need algebra, okay? So algebra, okay, we know where it comes from, right? So I think, I mean, we are living at this now crossroad where we need to use algebraic topology techniques to do communication, control, machine learning. This is the single most disruptive technique because it turns out Bengio, in our community, the Bengios of our communities are going this way, okay? Again, this is where I recommend my students to work on now. This is where you should actually focus if you really want to make an impact. More difficult, but more rewarding. And again, here, my goal is really what? Is I want to go beyond recognition. I want to do reasoning. So reasoning via causality, using via logic. So, you know, logic comes from Ibn Sina, for example. That's something we tend to forget. So Ibn Sina is famous for, you know, Qanun Tib, right? Actually, if you go check his life, I think his impact maybe in logic is even more important. I don't know, maybe it's just me who is biased these days. So you find me these days reading actually the history of Ibn Sina. Because in fact, the modern literature, the European literature does not cite him. Now when I'm reading logical papers, I find his works actually there. Anyways, some history, always good. And of course now for this algebra, what do I want here? This algebra that we need here is actually not the algebra we were taught in school. In school, the sign equal, 1 + 1 = 2, it's a very misleading, very narrow mind of notion of equivalence. When we say two things are equivalent, we are just taught numbers, you add them, it gives you a number. We need to do the same thing now here, but at the level of shapes and topologies. Combine two topologies, give you a different topology. That's essentially what we need, because now, again, we need to, you know, we need an algebra where I can manipulate my, you know, my object. So my object, again, could be an image, a state, a policy. How can I make this image now, map it to a topological space, right? And manipulate the topological space by rotating, by finding symmetries, right? This is where you need to now read more literature. So for example, you know, for me before 2 years ago, I never heard about notions of homotopy equivalence, right? This is when you say, you know, two spaces are the same, but same in terms of what, right? Homeomorphisms, these are concepts coming again from you know, topology and algebra. We actually need them, okay? And why we need them is because, in fact, this is where you need to step back. So CNN, right? Where is CNN? Here. CNN has a notion of translation invariance. You move a bit the pixels, it's still the same dog, right? You turn it, it's still the same dog or cat. It's actually one sort of invariance. It's a very easy invariance. It's the group of rotation and flips, right? And translation. But today we use it because Yann Lequin, I don't know, 20 years ago he found this, so on and so forth. But now what we want to do is to go from, you know, acting on a set, so this so-called group invariance or equivariance, to acting on topologies. Okay, this is the next kind of leap we have to make, because with this now we are thinking again categorically. Okay, we are thinking in terms of topology, and with this you go back and study why CNN was so powerful. Because today we talk about black box, white box. The black box is because you close your eyes, you feed your CNN, you go for coffee, you come back and you get results. But now we need to actually go back and understand what's the object acting on the set of image, that anytime I turn the image, it gives me the same object. Okay, again, in the case of an image, it's easy. But now we go beyond images, we go to different realms. I have now states, so people working on, you know, multi-agent RL, they deal with states, actions, reward. That's my object now. So of course, what's the invariance that, you know, allows me now to say two states are the same, right? This is what we need. And again, this is really, again, a step back. It turns out, essentially, as I said before, my community needs it, well, those who are aware of it, because this requires a bit of a mindset change. And Bengio and others, they actually talk about it either using System 2 language or other type of, okay? This is, I think, my last slide. I don't know, this is also a very, very hot topic nowadays. It's a topic which is a bit confusing for people because they don't understand the mathematics behind it. So Shannon, of course, that's what you, I think, you work on, right? There, what you need to do, again, is to put your lens of topology. So in the case of Shannon, information is a scalar. Okay, it's a numerical value. It's the entropy of X. Okay. In semantic communication, no. Information, we talk about structures. We talk about topological spaces. Okay, you see the difference now? This is only statistics. Here, no, we need these 6 ingredients I showed you before, because I need to manipulate. I need to compose, add objects, okay, to come up with new objects that do not appear on my training data. Okay, so this is the, it's like language. Language is both compositional, right, and algebraic. So that's essentially what we need to do. Here in Shannon case, the decoder and the encoder are the same, meaning the decoder tries to inverse the encoder. We don't need to do that. That's a waste of resources. Now in semantic communication, no, I need to extract the semantics from the data, communicate it, encode it, and then the receiver doesn't have to decode it at the bit level with the super high packet error rate. No, it doesn't matter actually, but it just needs to learn the concept. What is the concept that the sender is communicating to me to solve a task? So task here could be something you have in mind, right? But really, it's all about, again, notion of sameness, right? And again, topology. And I think that's actually my last slide. So of course, acknowledgement to everybody. And happy to take questions. And
Thank you very much, Professor Mehdi Benis, for this talk. Very interesting, very exciting. If you have any question, maybe 2 or 3 questions. Yeah.
Thank you, Prof. Benis, for the very insightful presentation. So I would like to, I have some questions. The first one, in the server-free approach. The server-free approach. So what is your hypothesis about the workers, the clients? I mean, the server-free approach. Before, wait. So what if, my question is about the workers. What if the workers, one of the worker is not willing to contribute or to collaborate in the training, or it is a malicious client and so on? And also, the second question is another part. You said that we cannot always rely on the accuracy. We have many metrics. So how to decide about which metric we will choose, in which context, etc.? Yes.
Okay, yeah, thanks for the very good question. So the easier question, the second one, it all depends on the requirements of your application. Some applications require energy by design, right? I don't know, this could be your watch, could be, I don't know, microcontroller. So they would rather maintain the lifetime of their battery than to have a very accurate model. So it depends. I mean, for us here, we don't really mind. So, but once you go to the application, you need that input to either choose one of them, forget 3 of them, take 1, right? But usually, again, just the reference for you should be the human brain, right? We are energy efficient, 20 milliwatts, resilient, reliable, accurate, So can we find that trade-off that we can now put in our machines? This is the key, because sometimes if you are resilient, therefore you are reliable. If you are resilient, therefore you may be also energy efficient, right? This is the idea, actually. As regard the first question, yeah, so I don't know if you work in game theory, so this kind of research here assumes from the beginning that all the devices are not malicious, they are honest, okay, and the server may be the one which is malicious, okay? So now the real approach now, 3-4 years later, is in fact also you need to bring in the notion of incentive mechanism design. So if Rashid Azouzi was here, for example, we have a project on that, you need to incentivize workers to come and contribute with their model and pay them blockchain and whatnot. Yeah, this would be a more holistic approach than what's done here. I mean, this is again theoretically driven, but it doesn't mean that you can also do theory with this approach. And actually, our project with French, is on this. You need this motivational part because nobody will contribute, right? Yeah, yeah. And then you have coalitions, maybe, you know, coalition gains are interesting here. I can join this coalition, leave another one. So blockchain also is behind the corner. Yeah, there's a lot of yeah, open problems.
Thank you. Other question?
He always has questions in my talks. Good ones, by the way.
Thank you very much. It's very exciting talk and lots of years of work. Very impressive of the quality and the result that have been obtained. Maybe I start at the end of the slide when you expose the global vision, and we should include, for example, topology and things like that. Maybe from I don't know, from what do you think from your point of view? Most machine learning are based on gradient approaches. Maybe by changing spaces, if we are going in another no Euclidean space like Riemannian, maybe we can still have similar properties, but it's not sure. Finding the best spaces for your data is not so, I think, easy. So easy, yeah. Maybe also we should think outside also the box, that we don't know how most models are working. Maybe there's other approximation, like making the allusion to a different equation. That's exactly. You get the point. But really, it's a starting point for.
This is where if I have power over all Moroccan students, I would push them here, because here even a baby step is a huge. Okay, instead of again competing on federated learning, and next week on archive you find somebody did better than you, and because he has access to GPUs and you don't have, right? But regarding your question, also here it's very important to be multidisciplinary, but to mean it, not just to say it because proposals like it, right? When you talk to robotics people, actually they do something similar. For example, motion planning of a robot, if you do that planning over the Euclidean space, you fail, right? Therefore, you have to go to this topological space, it's called configuration space, and plan over there. And that space is full of, fantastic, shapes and geometries. For example, you cannot have, holes along the way, right? And they tell you this path is the same as the other path, not in Euclidean GPS coordinate, but again, in that space. To me, it unlocked a lot of things in my brain, because I'm also like you, everybody. Sometimes you do system one, you do things you don't know why you're doing them, but because everybody else is doing. But yes, this is very difficult area, and in fact now there's a fundamental mathematic theory here. If you have time, please go and study it. It's called category theory. Category theory is the mathematics of mathematics. This is essentially people who they think really in abstract way, but not using the word abstract. So the word abstract is mathematical. It's not just philosophers or something. Yeah. So people who know group theory, group theory maybe. Yeah, you studied probably this in your Mathsup, Mathsp, right? We studied linear algebra. We didn't study much maybe abstract algebra, right? So, or maybe for some of you did. But the next step, when you go from groups, because it's all about structure. Sets don't have structure. A bunch of sets. Yeah. When you add structure, you end up with a group. Now group with structure, category. And now I can tell you there are people investing a lot in this. So it means you go take a book, read, and derive, model, apply, and I think it will pay off. Yeah.
Thank you very much.
Thank you. Thank you. The last question.
Thank you so much. My question is about this recommendation, this conclusion. You are talking about using more mathematics in the learning, and more topology. And I'm using little bit of information geometry.
Very good.
Talking about manifolds.
Very good.
But with images. I'm wondering how we will model CNN as a manifold. You talked about manifold mix-up.
Yeah.
So how are we gonna do this?
So what's your question is, so manifold mix-up actually is a technique proposed by Bengio, right? So the idea, you can do mix-up in the data space, meaning you take cats and dog images and then you do a weighted sum of them, and it gives you more data. Or you can do it in the internal latent space. It turns out this is where now things get confused, because when people hear space, it's either, for me, it should be topological. In manifold mix-up, it's not a topological space. It's a vector model. Problem with vector model, you don't have structure, right? So this is something to keep in mind. But if you work on already information geometry, is the right step. But just there's an ocean of techniques there, because ideally what we want to do. So if you ask Benjio, I follow his works a lot actually. His $1 million question, next time he comes to Morocco, you can ask him this, is to learn semantic categories from data, which means is what the baby does, okay? It learns concepts by interacting with the world. This is the same, this is different, and you end up with a repertoire of concepts, abstract concepts. These are not, it's like ontology, right? And then you use it later on to solve, daily problems, or communicate with another agent, a baby, or.
So the idea is to use geometry, maybe Riemannian.
Riemannian is just one of them. So Riemannian manifold is one, but you need to maybe.
Can we use it with CNN?
I would use it actually as a diffusion process. If you're familiar with stable diffusion, this media stuff you see, for example, now this stable diffusion process. What is it? It's a partial differential equation in the topological space, right? So you could do it for Riemannian, right?
Thank you so much.
Yeah.
Very interesting. Thank you.
Thank you very much, Professor Mehdi Bennis. I know you have more questions, but you have in the coffee break you have a networking session. We can discuss with Professor Mehdi Bennis. Thank you very much.
Thank you very
Mehdi.
much.
Thank you.
Thank you.
Before switch to next our keynote speaker, I will give you some souvenir from the WINCOM conference and ENSIAS, given by the director of ENSIAS, some trophy. Maybe we can go here. And some attestation.
J'ai discuté avec vous la partie isomorphisme. Ça m'intéresse. Très bien.
So, Dr. Tashkin, are you with us? Your mic is muted. Dr. Tashkin, are you hearing us? So, can you unmute your mic, please? La connexion. تقصوني عليه؟ Semantic communication. Philosophical question. واش كاين شي واحد خدام فيها ولا كاين شي واحد خدام فيها دابا؟ نبداو فاش هاد structured data. Good day, Dr. Tashkin. Are you hearing us? So your mic is muted. So kindly unmute your mic, please. We cannot hear you.
Can you hear me now?
Yes, yes, Dr. Tashkin. So,
Is it okay now?
yes,
Yeah,
but the video is not in real time, so your photo is still stable. Yeah, now is okay. So,
we can see my presentation. Hello.
yes, your presentation, yeah, we can see it, yeah. So give me just a couple of seconds to introduce you, and then you can start your speech. So, hello everybody, and welcome to the next session of Keynote speakers. So our second speaker is Professor Dr. Tashkin Gafzoglu from Gebze Technical University in Turkey, and he is also the Dean of Faculty of Engineering in such university. So mainly Dr. Tashkin and the University of Gebze in Turkey is well known to be the one specialized in drones and UAVs. It hosted a lot of companies and firms that are interested in modeling, building, and manufacturing drones and applications with the relation with drones and other applications. And Dr. Tashkin is his main field of research is remote sensing. So he was interested in multiple fields of research around this thematic, including mathematical modeling of artificial intelligence, neural networks, object image-based analysis, and also climate change analysis, to the best of my knowledge. So today he is going to share with us the latest result and finding of his project. So without delaying more, so I'm so sorry, Dr. Tashkin, we are delaying your speech, I guess 40 minutes. So the floor is yours.
Thank you very much. Good morning to all attendees. It's an honor for me to give a speech today, as you respected and distinguished researchers. I'd like to convey my sincere gratitude and thanks to the organizers of this event for their invitation. I'm sorry that I couldn't make it today. In fact, I have been working on artificial neural networks, machine learning algorithms for about 25 years. And I have been focused on the role of feature selection and hyperparameter optimization for neural networks. Lately, we published papers on superstructural neural networks as well. And I have publications on the use of remote sensing images, investigating landslides such as wind change detection, forest applications, and climate change effects. I'm very grateful to my team in my project. We finished the project, and I will share the results of the project here as a part of the results, in fact. Yesterday, the results were published in Advances in Space Research Journal, and we can read the details there as well. Today, not only the theoretical background of machine learning, feature selection, and their use, I'm going to explain about the project that we conducted about the last 3 years. In this project, we focused on the extraction of complex filtered fields and I'm going to explain why they are important for Turkey and world as well, and how can we improve our knowledge and make real accurate results or reports that we have, which aspects we have in our countries. This is the project we conducted at my project team on the field. It just ended in October, last October. We were together with part1 University and an special institute for poplar and fast-growing forest trees. Outline of my speech will be focused on introduction, latest study areas. I'm going to explain to you the datasets as well. Then, the first time in the world, we produce spectral libraries to detect poplar types, poplar species and clones. I'm going to show you the results from the field that we collected and the methods. Here in the methods, we are going to talk about machine learning algorithm or deep learning algorithm. And then we will have three approaches for classification from the information we gathered on the field. The first one will be pixel-based image classification. This is the traditional way of classifying images. And the second one is like the new agenda for the researchers. Is like object-based image analysis. We can see in all research areas, it's a popular area now. Instead of pixels, we use objects in classifying or identifying objects. And the last one is cloud-based processing of images. And we conducted using Google Earth Engine. And I'm going to present the results and explain how it works. Then I will conclude giving my results and conclusions, and then mention about the ongoing and future work. Why poplars are important for us? Industrial plantations are created on a large scale, not in Turkey but in the world. If you look at which countries are using poplars for the industry and cultivate them, the first one is Russia, then Canada, USA, and China comes the first four. Poplars are a member of the fast-growing trees and one of the most productive trees. You may have heard of them, but for me, I'm a specialist, but I work with forest professor from forestry department, and these trees, like 8 to 10 years later, they will be cut down. That's why they are very fast-growing trees and very good for industry, especially about paper, making papers and in the industrial areas. In Turkey, we have about 145,000 hectares of poplar trees. The advantage is that they can be used in the rehabilitation of forest ecosystems, restoration of degraded lands, and mitigation of climate change. We can use them. For this, for the importance of them, what we have to do is to determine or monitor all these poplar cultivated areas, and we need accurate images, accurate results. Therefore, we need machine learning techniques and deep learning techniques to map all these areas and produce real, accurate, and reliable results. For this aim, what were our objectives in this project? First of all, we needed to collect spectral reflectances of the poplar species at three phenological stages. In the early stage, and when they are mature, and then the end of the growing season. From these spectral libraries, we can use our information to detect and understand what is going on the field. Without going on the field, if we have this one, we can use as a guide. And then we use two types of images. One of them is the most effective and the most productive images, view 3 images. We had all 16 bunches of them, including the short waves, and the freely available Sentinel-2 images you can download from Copernicus system, Copernicus Hub. From the spectral library and the collection of other data, other inventory data from the field, we can use pixel-based and object-based approaches to produce the thematic maps for regions or for Turkey or for other places in the world. We use optimization techniques to determine the segmentation parameters, because object-based analysis is dependent on the quality of segmentation. Therefore, you need to be careful, and you have to use optimization like Taguchi optimization or others to optimize, find the optimal set of parameters like hyperparameter optimization is made. And then we compare the results of machine learning and deep learning classification results. One thing is popular nowadays is to explainable artificial intelligence or explainability or any other methods that you use. This is a core topic now, and it's like opening the black box. Always people mention about this, and in this study we use the SHAP analysis to understand what the model focuses on, which parameters were most effective. I'm going to show you the result. There are 3 sections that you have to concentrate to explain a model. First, when you are entering the data, what model learns, what inside the model, what parameters, how the feature space changes, and in the last part, when the model learns the characteristics, inherent characteristics of the problem, what is inside the model, which parameter is most effective or most weighted one. I'm going to show you. And the last one is to investigate the usability of Google Earth engine and how can we produce the free data, using free data, how can we produce thematic maps from there. In the study areas, we have 4 specific regions in Turkey. They have different types of species, popular species, and we worked on them. And but in this study, we focused on the area in Sakarya district. It's we call it Akyazı region. It was close to Istanbul, and there was only one clone type. It's called Samsun. It's produced in Turkey. And the other section, the other areas, I'm not going to present here because we don't have much time to show all the results here. This is a picture from the study site. You can see how it looks in August and November. In the middle of the field, in the middle of the picture, you can see the young poplar trees. They are like about 1 year, 1.5 years old. And the others is about 8 to 10 years old. One thing in the forestry is agroforestry activities. Nowadays is very popular, and it is popular with the poplar trees as well. If you have a poplar area, you can use agroforestry, agricultural activities. This makes a problem for remote sensing people, you know, because we don't have only the trees, we have other features in the land use, land cover features under the trees. That's why when we have a spectral reflectances, it's like a mixed up. And in this time, you would have a very high resolution image to have a pure pixel. Otherwise, they are all mixed up. In the case of sentinel images, we have 10 meters spatial resolution. That means every pixel covers about 100 square meters area. These are the images from the field that we collected data sets, data from the field. We have 2 approaches. First one is measuring the leaves, spectral reflectances of the leaves to understand their differences. The other one is the measurement of the canopy. When you are measuring the canopy, you have to go up and measure like what satellite sees. These are the pictures from the area. Now we have two types of images here. One is like 1.2 meters resolution, World 3, resampled. The others were resampled to 1.3 meter as well. And the central images, we use 10 and 20 meters resolution ones, and we sharpen them using special algorithms to make them 10 meter resolution. Now, in the field, we had to collect spectral reflectances. You can see one example here at the bottom of the screen. Water absorption bands here, and you can see how a vegetation behaves. This is a spectral signature of any object, but this one is specific to poplars. This is the first time we are about to publish these results. We have 5 types of trees. They are all poplar trees, but as you can see, for human eye, they are all the same green ones, but when you measure them out of the scope of our eyes, you can see that they are different, behaving different, especially the near-infrared and short-wave infrared lesions. Now, we take this information, especially here, we take this information as a reference, and we go around and make the models, teach the models how they can differentiate all these trees. In the classification part, it is important that you use representative data sets. We divided our 70% of it for training, and the other parts is like validation and test data set. It's like a common ratios, but it is important beforehand to make a representative data set to go around, to go forward. Otherwise, you will fail after the training process. What machine learning algorithms we use in the study, I'm going to mention about them. The first one is a supervector machine. It is a bit, let's say, a bit the older one compared to the other one, latest ones. Supervector machine is using a kernel trick. I'm sure you know about it. What it does, it transforms the feature space to a higher dimensional one. Those it can find an optimum hyperplane. It is usually a nonlinear one to differentiate, to find the hyperplane to separate the classes, all classes. It's in fact originally developed for 2 classes, but you can improve it to make it for you more classes. Here we employed it for all the datasets, and we got very good results with this method as well. A bit new one is random forest, that is very popular nowadays in every areas. It's a decision tree based ensemble learning algorithm. It constructs a multiple decision trees, and what it does is use the bootstrapping aggregation. It divides the training data into different parts and combines the results into a one. It's like an ensemble learning model. Another one is, in the study we use, is rotation forest algorithm. It is an improved version of random forest. What it does is get benefits of principal component analysis. As you know, in principal component analysis, we have a chance to eliminate the correlation between the what they call bands or the features. If you have more features and they are correlated, you can reduce your accuracy. That's why when you use principal component analysis, you can eliminate all the correlations in the data set. And the rotation forest gets this idea and used on the random forest idea. And the next one is the convolutional neural networks, deep learning model that we used here. I'm sure you may have heard it and used it maybe. There are many types of it used for object detection or classification. Here we are focused on classification. That's why there are lots of ready-to-use models like AlexNet, ResNet. But here we designed our own model to make our classifications. I used to, model every problem with artificial network simple like multi-layer perceptron. But nowadays we have more deeper models with different activation functions. In the case of CNN, we have more dimensions and more layers to model our problems. As you can see, we have convolutional layers, flattened layers, dense layers. We can increase the size of them, number of layers, and then produce very good results. Sometimes we can use it for the feature selection purposes as well. Here I have to give you a short introduction about what is pixel and object-based classification and why we use them. First of all, pixel-based classification is the first traditional type of classifying or images or extraction information from images. The images were like kilometers spatial resolution, but nowadays we have 30 centimeter images from satellites. And in this project, we collected data from drones as well, UAVs. And we have like 2 centimeters resolution for images. And that's why we have a big data problem and we need more sophisticated algorithms to model. When you are handling pixels, you have millions or billions of pixels to analyze. But when you concentrate on object-based image analysis, you are classifying the object, not the pixels. Objects are formed by homogeneous and adjacent pixels, and instead of, let's say, billions, you have 100,000 objects to classify or identify in the images. Here you can see as a result, if you have a pixel-based classification, the result will be salt and pepper loop, It's not a real type of presentation. That's why its new paradigm is to use object-based classification is like more realistic way of showing the parcels or the areas. Because in the other one, you have lots of points that are different. This one cannot be used to estimate the area covered by trees or agricultural products. That's why nowadays we use object-based classification, and it has other advantages that I will mention later on. Let's move on to pixel-based classification, traditional one. What we do here? First of all, we went to the fields and collected spectral reflectances of the types, non-covered types in the field. What are they? It's like corn, pasture, poplar, water, road. These were in our city area. We needed to collect their real reflectances and calibrate our images and teach our algorithms what are these classes and how we can classify it. All the reflectance collections were done with the AST field spectrum measurement. It's a spectral radiometer. It's a full range one. You can see in the image at the bottom the reflectances of all of them, like hazelnut, corn, and pasture. You can see their differences. For the worldview tree image, when we applied 3 machine learning algorithms, we got about 90% accuracy. But when we look at the poplar and young poplar specifically, we will see that it's about 95% accuracy we can reach, especially for younger poplar areas. It is important for us, because this is a very good data set, including 8 additional spectral bands, short-wave infrared bands, we could separate poplar and young poplar trees. This is a specific problem. It is impossible to do this with the classical images. That's why with tree, we could manage that, and we could separate over 90% accuracy. The same tree type, young one and the mature one, we can separate from each other. And this is the classification result from the field. As you can see, these areas, young poplar, showing the young poplar areas is like 1 or 2 years old. The leaves are really different. And the other areas here, you can see they are poplar areas. You can see the road here, the river here. And as you can notice, there are salt and pepper look. You can see here, because this is a pixel-based classification. In the fields, there are rows between the fields, and you can see easily. The resolution is 1.2 meter. That means every pixel here represents 1.2 pixels. When we do the analysis with the sentinel-2 images, the same area, exactly the same area, this time we had this problem because our pixels are now 100 square meters. We couldn't separate poplars from young poplars because we had little information, less bands, spectral bands. That's why we combine them into a single class, but as you can see, the accuracy is quite high. It's 95% here, 95% here, almost. The classification accuracy is over 91%. And here, especially we should focus on F-square values. It's the harmonic mean of producers and users' accuracies. You can see that, especially for water and hazelnut trees, very good accuracy we can get. This kind of accuracy gives the advantage of estimating very accurate thematic maps and estimating the total area. Sometimes we use it for the precision farming to estimate how much production we can get afterwards. With the random forest algorithm, with the sentinel-2 images, we can get this for the same area, this image. You can see the difference because the pixel size is different, the areas are larger. And these parts, you can see the shadows. This gives a glimpse of idea that you have high trees here. Because of the sunlight, there will be a shadow area. Now, the object-based classification results, I have to mention shortly about what it does, and it's like a new paradigm analyzing high-resolution images, spectral, spatial, and textual features of objects considered altogether. Homogeneous ones are merged, but you need the criteria. How can they merge and find the optimal scale, optimal objects? Because the optimal objects give you the highest accuracy. Otherwise, the quality will undermine your results. Two major steps we have in OBIA. We call it object-based imaging OBIA. First of all, we conduct image segmentation. We segment the images using region-based or other algorithms, but popular ones are usually the region-based. Here we use multi-region segmentation. You could use other algorithms like watershed or other algorithms as well, like mean shift. But the most popular one is multi-region segmentation, and we apply it to our images here. After the image segmentation, that means you created your objects, which are very homogeneous inside and heterogeneous to other objects. We go forward for classification. In the segmentation, multi-region segmentation you are using, you have to set 3 specific parameters, major parameters. These are shape, compactness, and scale. Scale determines the minimum size of the segments. That's why it's very difficult to decide on an image. We have papers discussing this issue, and other researchers are writing papers on how can we decide which scale value will be the optimal one for an image, because for forestry area is different, agriculture is different, and built up area, it will be a different value. As I told you, the quality of segmentation directly affects the resulting classification accuracy. Compactness and shape is, compared to the scale one, is a bit lower level effective ones. That's why usually they are used, they are set to fixed values like 0.5 or 0.7 in most studies, because their effect is only the construction of the edges of the objects. But the scale defines how big our objects will be. For this purpose, Dragut and his friends developed a model, and then they improved it. It's called estimation of scale parameter. It's from a published paper. This tool you can use with the accumulation software, if you have one. In the accumulation software, you can use this algorithm, the tool, to estimate the optimal scale value. I will show you the graph. It is on local variance change. It's based on local variance change. What it does is it iteratively estimates values for scale, different scales, and then estimates the local variance changes. Here you can see in our data set, this one, the blue one, is the rate of local variance change. When we get the optimal point, it was told the first peak or second peak generally, but here we got the first peak is 40, is the optimal scale value we can use for the analysis. This tool you can download and use in the Ecognition software. You can integrate it to Ecognition. The other parameters is that will be fixed parameters, 0.5 or 0.7 were fixed and used for the estimations. But for the scale one, we used our data set to estimate the optimal value as 40 and use these values in the estimation of objects. The next stage in object-based analysis is to use feature selection algorithm. The reason for this is in the pixel-based classification, you only the pixel values. We call them digital numbers. But in object-based classification, when you have objects, you have the mean of the objects. That means if you have 100 pixels in objects, you can estimate the minimum, mean, maximum values, or standard deviation of these values, or other indices. You can estimate the length of the objects as well. There are lots of features that you can estimate. Here, I will show you, we had 88 features. If you go forward with 88 features, you will need more training samples. This is the basic principle. If you are using more input features, you will have a bigger network or model. That model will demand more training samples. And if you are using correlated data, your model will fail after a point or will be over-specific. That's why for the generalization capabilities, you have to increase, you need the most important features. That's why we used, here I'm going to talk about chi-square algorithm, but we use random forest Gini index values as well. But I'm not going to present here. It is in our project report and in the publications. You can see the results as well. In the Shizuka, everyone, I'm sure you heard of it, it's like a statistical test, but you can use it to estimate, to evaluate the correlation between two variables and determine whether they're dependent or correlated. From this point, you can estimate how the features were correlated, how much they were correlated, and it gives you the importance list. You can get it from them. Now we had 88 features. You can see the list. Let's say we have 16 bands of word with 3. We have mean band values, maximum, mean, grade level, corpus, matrix, standard deviation, intensity, saturation, and DVI. I'm sure you have heard of it. It's normalized vegetation index, shows the health of the vegetation. Green chlorophyll index and red chlorophyll index, these are all showing the health of a plantation. Area of oxygen and length of pixel as we use as well. That means we have totally 88 features, but we cannot go through with 88 features. We need the most effective ones. That's why we employed this C-squared algorithm, and we selected 38 of them. The algorithm told us that these are the most important ones, and we went forward with these important features. Now we have almost 60% of the data set is gone, features are gone, and we can get even better results with the previous one. In that one, we say this support vector machine results, random forest results, and rotation forest results. Here, the best result was given by support vector machine, is about 92% accuracy. If you look at the poplars and young poplars, the accuracy is really high. Here, poplars about 93%, 90%, 92%, and 97% for support vector machine. That means we are over 90% is very good high accuracy level. 97% is like excellent recognition with World 3. Why we can get these high results? Because we collect data on the field, we know the problem, we know the field, and we use feature selection and other algorithms to improve our data set, and we use machine learning algorithms with the optimized parameters, like hyperparameter optimization, as you will see in deep learning algorithm as well. Now this is the result with the Worldview 3, when we used, this is the best performing one, support vector machine. The results of this, as you can see, all fields are clearly determined. Now, as I told you before, the importance nowadays is to explain the model. Machine learning model, deep learning model, any model we use, except for the linear ones like logistic regression, or they are very clear to explain. But when you are like a black box method, what happens inside, you need a model to explain their importances. This is called a Shapley analysis. SHAP analysis is a solution developed in cooperative game theory. Now we use it in our scientific research. SHAP analysis estimates the expected marginal contribution of a feature among all features. It's like a weighted average of marginal contributions. I suggest all of you to analyze your models at the end of the learning stage. You can check which feature, which input was most important. You can analyze using this tool. For the Sentinel images, these are freely available for Copernicus. The European Space Agency serves them. You can see the accuracy level is for the poplar, because we combine, as I told you before, combine poplar and young poplar. It's about 99% accuracy for the poplar. The accuracy level here with the random forest, the best one is about 95% classification accuracy we can reach. This is the result of the thematic map we produce. Now, when we come to the deep learning classification, the most popular one nowadays, you can see in publications, we constructed a special CNN model. This is the general view of it. We have the convolutional layers, latent, dense, and dropout layers, and you can see here all the parameters we set. For the convolution layer, we had 4 layers inside, and similarly, flattening and dense layer, we had another 4 layers. For activation function, we used ReLU and softmax. Dropout ratio was set to 0.1 and learning rate, etc. As you can see here. And the total parameters in the training stage, we used 87,627 parameters we had to solve in convolution neural. This is like a solution, unknown parameters that were estimated with the training data sets after the training stage, of course. Now, this is image of showing our learning stage. You can see the training loss and accuracies with the validation ones. Both training and validation losses were controlled here to avoid overtraining and to make a generalized network. As you can see, the training process converged after about 180 epochs, and we ended the process after 200 epochs. About 95% model accuracy was obtained in the training model, as you can see. Now, what was the result with the CNN model that we constructed? It's not a very complex model. Nowadays, they call it very deep convolutional neural networks. Deep learning, very deep learning. Ours is, I think, is like a deep learning algorithm, not very complex one. The accuracy, overall accuracy, was over 95%. Here, again, young Poplar and Poplar were over 95% classification accuracy. This is really high quality results that we achieved. Sharp analysis we conducted for deep learning results as well. Deep learning is like a black box because it's a neural network type. We always read this and write in our papers. Here you can see overall the model outputs, which inputs, which features were most important. These are the bands of Vertex 3. And for Poplar and young Poplar classes, you can see that short wave bands, this is like an extra band, so you have to pay extra money to get them, by the way, when they are selling it. Vertex 3 short wave infrared bands are very effective to distinguish Poplars from the other classes. This is a really important result to analyze what is going inside the model when the model learns the characteristics from the training data and set the boundaries. Now, when we come to the cloud-based classification, our aim was to teach the institute people to use Google Earth Engine with our codes, or they can include with their codes, estimate Poplar cultivated fields themselves. It's an automatic, we are making an automatic tool, only the running the code with the different areas. You define the coordinates of the areas, run the code, and you will have thematic maps. Google Earth Engine combines multi-petabyte of data. I'm sure you know Landsat, Sentinel, and MODIS data. They are very common data and they are freely available. You don't have to download it. You don't need any software. You don't have to pay money to all these commercial software to run any model, even the deep learning models, random forest. You can run them on cloud-based using Python or JavaScript code. You can write the code and run your code to estimate all this. What you can do change analysis, disaster mapping, trend analysis, and many types of research at global scales. This is the result for Akyazı district. This is a full area we run with our code. You can see it's a new one. At this year July, we had the popular areas voted. Only 5 classes we had here because it's a large area. We wanted to detect our popular areas, popular cultivated fields. You can see here is like accuracy almost 95% using the code, freely available data set, no software, only running our code on cloud-based system. We can estimate for each district. We can make these maps easily. And here we use random forest as a machine learning algorithm to estimate our classification results. Okay, when we can come to our conclusions. First of all, object-based classification outperformed the pixel-based classification approach about 3%, as you can see from the previous results tables. Tree-based algorithms were more effective than super-vector machine in general, but the CNN model produced the highest classification accuracies, like about 95%, it's like 4% more improvement than machine learning algorithms. With the increased spatial resolution and spectral resolution, with the use of freely available sentinel images, broad coupler class, that means we have all types of couplers, we can classify with 95% accuracy. Chi-square eliminated about 60%, 57% of the data sets, but still produced very good accuracy results compared to the pixel-based classification. And the SHAP analysis really helped us to understand what was important, which features were most important to model or to get the inherent features in the data sets. And lastly, the Google Earth Engine platform was very effective tool to monitor popular cultivators and produce easily the maps, thematic maps, 5-day basis. Every 5 days you can get the new images, sentinel images, and you can create the thematic maps only by running your algorithm again. Okay, ongoing and future work. What we are going to do and now what we are about to do. First of all, our aim is to use VAV datasets, images, with deep learning, 2D, 3D, and object-based deep learning algorithms to automatically detect popular trees and count them. After counting them, because we have a 3-dimensional dataset, we can estimate the volume of timber easily. This is one aim that we desire to produce, and we are going to give these results to Popular Institution. Enhancing our popular spectral library, we have now for 5 species, and in Turkey there are 3 more species that we want to collect and make a very nice library for everyone in the world that can use in their research. Object-based deep learning for classification, establishment of a cloud-based system, and using more robust feature selection algorithms. Here on the right, you can see another example of application that we have done on our VAD images. In our campus, we could catch stone pine trees and count them. Now we are on the way of applying it to poplar trees. We had the UAV images. Now we are running all algorithms and catch them with high accuracy and count them and give reports for every field. the government and will use the data, know how many square kilometers of land and how many timbers the plant they have in their stock. These are the publications so far we produced from our projects. And as you can see, the first one, Advancing Space Research, yesterday, it was published online. You can check from Elsevier system. Thank you very much for giving me this opportunity to share our results. Not only the theoretical background, I wanted to show the latest developments in remote sensing area with the forestry applications. Thank you very much for being here and listening to me. And I wish the conference will be a very fruitful one. And the next time, I hope I will be in Rabat with you. Thank you very much.
Inshallah. Thank you very much, Professor Tashkeen. Actually, I was waiting for you to visit us. I guess next month you will be in Morocco, inshallah. So looking forward to meeting you in person here. So now we'll move to the Q&A session. So briefly, we'll take 1 to 2 questions. I guess we are delayed enough the lunch. So yeah, please.
Thank you, Prof. Taskin, for your presentation on this very interesting topic. So actually, I have a question on the part of the SHAP analysis. You said that you used the Shapley value to calculate the most effective parameters. As we know, the Shapley value calculate the marginal contribution between different players to get maybe the most highest score or the most important players, depending on the context. So here you said that you are choosing the most effective parameter. So my question is, how did you choose the value function? What is your value function? And also the same question for the model explainability. So when you
Because the sound is not very well, it's like echoing. Can you repeat the question?
So I said on the SHAP analysis part, what is your value function for selecting the most effective parameter for Shapley value, the value function? And also the same question goes to the model explainability part. What is your value function for the future, for selecting the most important futures?
So I got first question, my second questions. I cannot hear. You know, it's really difficult to understand. Okay. For the first question, I can answer.
Can you take this one?
Sorry for the. The first question, in the SHAP analysis, which parameters, how do you define the most important one? This is similar to if you know CFC analysis for the future importance analysis. It's popular in last sensitive mapping and any sensitive analysis. If you have more features, you do the similar graphics. But the problem is, you have to have a threshold value. Normally, here you see, let's say for the popular class, we have the importance rates, right? It's like a weighted rate. It's like more than 0.8 is for the short wave infrared 1. But here, in almost all papers, I noticed nobody puts threshold. In most papers, you can use here, you will see this one. They will say that the contribution is over 0.0. That means something is important. There is an information. And they don't eliminate anything. If you look at the papers, if there is something here like 0.0001, they will still use that data set. I disagree with this kind of application. You need to have because I use neural networks and I know the problem of constructing a model with large size of networks. That's why you have to eliminate some of the inputs. Okay, that's why I suggest that using like 0.02 or 0.04 as a threshold and eliminate almost half of the inputs. Then do the analysis again. This shows you the irrelevant features or less effective features, we can say. You eliminate them and you will get a bit bigger of the higher accuracies, because best results only comes with the best ingredients, Best inputs will go to the best results. And if you try to use everything in your system, even if they conflict with each other or they have small contribution, your network will be very large and over-specific to a problem, and training such a system will be very difficult. That's why here I suggest SHAP analysis is one of them. This kind of analysis beforehand you can use it. There is with other algorithms as well. This one is after the model training, and there are algorithms you can use only the training data set before the model construction, and you can eliminate your data set. If you look at CFS algorithm, you will see the details, statistical analysis. The second question, I don't know because I couldn't hear. The sound is not very nice. But the first question, I think I answered.
Yes, thank you. It's about the Shapley value on the model parameter. If you talked about this at the beginning of your presentation. You said that you used SHAP analysis for the model parameter, not for future selection. How did you use that? What is your value function, etc.?
In the first part of my speech, I said the machine learning algorithms, especially the artificial intelligence one, neural network types, starting from multiple neurons, CNNs, any other method, they are called black box methods. For 20 years, everybody blamed neural networks to be a black box method. That's why sometimes they didn't know how to parameterize set the parameters, and that's why they got very bad results compared to some other simple algorithms. That's why, first of all, hyperparameter optimization is very important, and secondly, you have to know what kind of data you have to use inside the training process. You cannot use everything. For example, here I had only 16 one. The previous one we had 88 to reduce to 38. For that one, we had a bigger size of the network. For a network, the unknowns is the number of links in a neural network, How many interconnections you have, this is your unknowns. If you increase the number of unknowns, you will have a very big problem to solve. It's like not a it's like a polynomial, not a fifth version. It will be 10th degree. Instead of 5th degree, it will be 10th degree problem to solve. That's why you will need more data, more time to train it. That's why I suggest opening the box with SHAP analysis and other methods to analyze how it behaves with your problem.
Thank you very much. Thank you.
Question, Dr. Tashkin?
Yes.
Yes,
of course.
So, Dr. Benis, do you have any questions? So I guess we have to stop here, maybe. Thank you so much, and much thanks to the organizers for giving you this opportunity. And yeah, by the way, so we have prepared a gift for you. So it will be saved here until you're coming to Morocco, inshallah, next month. So this is a great bridge between the organizers and Gibbs Technical University. So looking forward to leveraging your skills in designing, modeling, and multiple application on those to be some exchange with professors and researchers here in Mohammed V University and other universities involved in this conference. Thank you so much, and
thank you, Professor.
Thank you so much.
Thank you.
Thank you very much.
Bye.
بالنسبة للأسئلة